So the continuous assessment, like I said, 60%, and the final assessment is 40%. The exams are clear. The assignments, we have a written assignment and discussion. So Baba Kurdi Bilin Bo Oyorun Bed. Assignment كان كليرا همانا نوسين بك اسي كاي نوسي لصدا 20 درجه كتي لسرا ابي سيري كونتنتي كورسا كبكي اليراكو كونتنت كيتيا سيري كونتنت كامبكا بابتك دو بابت كبيونديان بيكو هبي سي بابت كزور بيونديان بيكو ابي هر ابد لسري بنوسي كشينيا يعني بابتك تنها اگر ازاني اتواني فوكسي لسر كويتو بينوسي أو شر كشمان نابه أبين كان بيوندي بو parameters pertaining to computed tomography physics and instrumentation أبيز راستو خو بيوندي بكونتنت كورس كوه به أوش لا لكتشر كان ليرة أتياتي كونتنت كان إيه كلو بابتانا وكوت ما دو بابتي هالبجيرين أو بونوسينا كي عادة أمنوسينا كبيرة داما ناوا بو أوي هموينا كويت آخره فاينل درافتكي لهفتي دايما أبي سبميت بكري جون 6 بس بيش أوا لهفتي چوارما أمامي درافتي يكمي سبميت كان دواء أسايمنتك دانين لبلاتفورمي زانكو أتوان لي سبميتي بكن ئەوەی کە گرنگە بۆم هەفتەی چوارەمە ئەوەی کە تۆپیکەکە هەڵبژێری ئینترۆداکشنێکی کورتی لەسەر بنووسین هەنێ بەحس و شتی لەسەر کە بۆ نمونە پەیپەرێک دوو پەیپەر یان زیاتریان کەمتر وەک بۆ ڕیفرەنس بتوانی بەکاری بێنی یانە بێ بە کورتەکەی بڵێم خوێندنەوەیەکی کورتت لەسەر کردبێ و تقریبەن لە بابەتەکە تۆزە تێگەشتبی بزانی هی ئەوەیە کە لەسەری بنووسی و دیتێڵ و ئەو شتانەی باس بکەی لە ئاخیرەوە كأمما قبول كرت دواء يعني كأود بومن نارد بيتلم أمبابة باشا وبيوندي بدرس كمان وهايو أتواني بردوان بلا سري أجرنا إيميلك بوين يرم بونمونا أمبابة زيادة البيوندي بوشت خمان ونية يا بيوندي با يعني أو ديتيلي وزياد كيان زيادة البولة يعني يا باسي بك كبيوندي بدرس كخمان وهايبه فيدباكي بيدم لسرما بو هفتي دوها بۆ درافتی دووهەم ببورن درافتی دووهەم ئەویان لە هەفتەی حوتەمایە یعنی سەریە و ئیمێڵەکەیتەوە هەنێ معلوماتی زیاتر بۆ ئەسایمنتەکە زیاتەکەیت و ئێسایەکە تۆزە دیتیلترەکەی لە دوای ئەوە فیدباکێکی تەفسیلت پێدام بۆ ئەوەی بۆ فاینەڵ درافتەکە تەواو حازر بێ هەرچی ئیمپروڤمنت و ڕیڤیژن و ئەو شتانە هەیە توانین لە بینی هەفتەی حوتەم هەتا دەهەم بیکەیت و لە هەفتەی دەهەمە سەبمیتەکە ئەمە بۆ نووسینەکەیە سانتا ئێستا بۆ نووسین بۆ ڕێتن ئەسایمنتەکە هیچ پرسیارێکمان هەیە یان ڕوونە فەرموو
دکتۆر ببوورە یعنی لە هەفتەی چوارەما بەس ئەوەنە ئینترۆدەکشنێکە بۆ بنێرین بڵێن ئەم بابەتەمان هەڵبژاردوو بووی تۆ پرۆڤیکەی
تقريبا شتێکی لە بابەتەیە یعنی تۆپیکەکە هەڵەبژێری ناوی تۆپیکەکە کە هەڵبژاردووە وەک تایتڵەکەی نووسی ئینترۆداکشنێکی کورتی لەسەر ئەنووسی بۆ نمونە پەیوەندی بەم بابەتەوە هەیە و ئینترۆداکشنەکە تقریبا ئەگەر بە پاراگرافێک بێت کێشەمانی یعنی نیوپەڕێک دوایەوە نیوپەڕێک کۆتایی یان پەڕێکی دوای ئەوە چی لەسەر ئەنووسی بۆ نمونە بەحسێکت لەسەر کردووە پێپەرێک لەسەر خوێنیتەوە یان ڤیدیۆیەکت لەسەر سیر کردووە بۆ نمونە ئەڵێ لیمیتیشنی ئەم بابەتە ئەمەیە کێشەکەی ئەمەیە ئێمەمانوێ بە دوام چارەسەرای بگەڕێن یعنی پێویست ناکات زۆر بە شێوەیەکی ئەکادیمی و تەفسیل و ئەو شتانە ئەو بەشەی دووهەمیان بنووسی تەنها ئەوەیە هاتوون بڵێ ئەوەی کە لە فکر تایە و بەرنامەت بۆداناوە تقریبا بە شێوەیەکی ڕەف درافتێک ئەخێتە سەرەوە
پێویستە کا ڕفرەنس دابنین لێ هەفتەی چوارەم و حوتەمە یا بەس دێمە دایبین ڕفرەنسەکان بۆ
هەمە ئەمانەوێت لە هەفتەی حوتەمە بە دڵنیای ئەمانوێت چونکە من فیدباک لەسەرەوە دەم بۆ ئەوەی هەر ئیمپروڤمنتێکی بوێ لەو کاتای بۆ هەفتەی دەم بتوانانی چاکی بکەیت بۆچی چوارە ئەگەر لەسەریشی نەبێت تا ڕادەیەکی زۆر کێشەمان نییە بەڵام بۆی کە بزانم شتێکی لەسەر خوێندێتەوە ئەگەر پەیپەرێکیان ڤیددیۆیەک سیر کردو بە لینکێک لێ دایبنی ئەو باشتر
دەستەکانە خۆش ئازتم مای
سەرچە هیچ پرسیارێکی ترمانەیە لەسەرەوە یان چینە سەر بابەتی پرزنتیشنەکە بزانم پرسیارمان نییە بۆ پرزنتیشنەکە کە ئەویش لە سەدادەی لەسرە لە سەدادەی فاینەڵ گرێدەکەی لەسرە ئەمان چۆن چۆنیە وەکە کەوتمان ینی شتێکی گرنگ لێرە بیکەی پێش ئەوەی بابەتەکانیان یەکلای بێتەوە ئەوەیە کە گروپی خۆتان دەستنیشانکە بۆ نمونە بۆ گروپ دیسکەشنێک وتمان لە بینی 3 تەلەبە تا 5 تەلەبە ئەتوان لە گروپێکا بن یعنی 3 کەس ئاساییە 4 هەر ئاسایە 5 هەر تا حدێک ئاسایە بەڵام لە 5 نابێت زیاتر بێت و لە 3 نابێت کەمتر بێت لەو حاڵەتەیە چیەکەی ئەو بابەتەی کە هەڵە بژاردووە لەگەڵ ئەو هاوڕانێک کە لە هەمان گروپی خۆتان بۆ گروپ دیسکەشنەکە نابێ بابەتی دووبارەی تیابێت یعنی نابێت دوو کەس لە هەمان گروپ هەمان بابەتیان هەڵبژاردووە بەڵام ئەگەر گروپی دیسکەشنەکان جیاواز بوون ئاساییە بابەتی دووبارە هەبێت بۆ نمونە گروپی دووهەم یەک دوو بابەتیان هەڵبژاردووە کە هەمان بابەت لە گروپی یەکەم مالایی چوارەما هەیە ئەوان ئاسایی بەڵام لە هەمان گروپ نابێت بابەتی دووبارەی تیابێت تکایە تەرکیزکەنە سەر ئەوانە پێش ئەوەی بابەتەکەی خۆتان بە تەواوی یەکلایکەنەوە گروپەکە دروست بکەن ئەتانەوێت لەگەڵ کێ باسی بکەن دیسکەسی بکەن بۆ گروپ پرزنتیشنەکە بۆ ئەوەی دڵنیابن کە بابەتەکان دووبارە نییە چونکە بابەتی دووبارە لە هەمان گروپان نابێ هەبێت چونکە بۆ هەفتەی چوارەم کە ڕەفدرافتەکە ئەنێری ئەمەوێ ناوی گروپەکەشی لەسەر بێ بۆ نمونە ئەمە گروپەکەمان ئەوەیە و ئەمە گروپ مێمبەرەکەمانە 3 تا 4 کەسی هەیە یا 5 کەسی شتمان ئەویش ناوەکانی لەسەر بنووسن هەر لە خوارێ تایتڵەکەەوە بۆ ئەوەی کە سەیری بابەتەکانمان کردڵابینەوە کە بابەتی دووبارەیتیانە لە هەمان گروپ وازحامە
ئەوەش بەستێکە
بەڵێ ئەمە ینی باشە وازح باش چیمان ئەوێ لەم گروپ پرزنتیشنە لە گروپ پرزنتیشنەکەیە ئەوەی کە زۆر تەرکیزی لەسەرەکەین بۆ نمونە وتمان 4 کەس یا 5 کەس بەیەکەوە دانیشتن باسیەکەن بابەتەکەی خۆت بۆ 2 دقە 3 دقە باسی بکە وەک ئینترۆداکشنێکی تەفسیل بەڵام بە کورتی بۆ نمونە منم بابەتەیە باسی ئەماکە و تەرکیز لەسەر ئەماکە و کێشەکانی ئەم بابەتە ئەمەیە و ڕەنگە بەم شێوەیە بتوانێت چاک بکرێ یعنی زۆر زۆر لە بین ئەتوانین لە بین 2 دقە تا 5 دقە ئەوە ببڕێنەوە ینی لەوە زیاتر نەبێت لە 5 دقە با زیاتر نەبێت دوای ئەوەش ئەو هاوڕێی تەنیشت بە هەمان شێوە ئەوی تریشان بە هەمان شێوە ئەوی تریشان بە هەمان شێوە ینی هەمووتان یەک باسی بابەتەکانی خۆتانەکەن بە تەفسیلی و بە شێوەیەکی کورت ینی هەر کەسێک لە 5 دقە زیاتر ئەو باسکردنە تێنەپەڕێنێ تکایە لە بەریشی مەکەن مەیشی خوێنەوە ینی هەروەڕخکە بدابنێت ئاوا بخوێنیتەوە یان لەسەر سکرینەکە بخوێنیتەوە هەوڵ دەلی تێبگە ئەگەر نۆت و شتێت هەبێ وەک سەردێڕەکان کێشە نییە باسی بکەوە وەک وایە بۆ مجموعەیەک دانیشتوی باسیەکەی زۆر ئاسایی دوای ئەوە چیەکەن کە ئەمە تەواو بوو بۆ نمونە کەسێکتان پرسیارێکی هەیە بۆ نمونەڵێ من بابەتەکەی من بۆ شێوە بوو ئەو تۆش بۆ شێوەیە چۆن ڕەبتیان هەیە بەیەکەوە یان ئەو چارەسەری تۆ بۆ هەڵبژاردووە بۆ کێشە بۆ ئەم بابەتە منیش ئەبێت یان نابێت یان ئەگەر ئەو چارەسەرە بۆ بابەتی تۆ بکەین ئازەرە لەوەی من نادا یعنی دیسکەشنێک تقریبان لە بینی خۆتانە دروست بکەن بۆ زیاتر تێگەشتن لە بابەتەکە و باسکردنی بابەتەکە ینی تقریبا ڕووکردنەوەی بابەتەکە بە 5 دقەیەک ئەوی تریشان هەر کەسێک ینی نابێ هەر یەک کەس ئەو پرسیارە بکات و ئیترتەوە یاوە وەک چۆن بڵێ وەک پەناڵێکە دیسکەشن پەناڵێکە پێشکەشکارمان نییە باشە کاڵم پێشکەشکارمانە ینی تەرکیز تەنها لەسەر یەک کەس نییە کەسێک پرسیارەکە دوایە کەسەکەی تر دوایە کەسەکەی تر وەکو بڵای هەر کەسێک ئەبێتە پێشکەشکاری ئەو دیسکەشنە یان بەڕێوەبەری ئەو دیسکەشنە بۆ چەند دقەیەک بۆی پرسیار بکەن و لە یەکتر تێبگەن بزانن بابەتەکان چۆن چۆنە تکایە ئەم جارە شێڵێمەوە با لە بەرکردنی خوێندنەوەیتیانە بێ هەوڵدان هەتا ئەتوان با شێوەیەکی سروشتی بێ چونکە کاتێک کە وەرەکان نەخوێنیتەوە هەر دیارە یعنی شتەکە تەبیعی نییە یان لەبەرت کردووە یان ئەو شتانە بۆی هەوڵدان لێ تێبگەن و بە باسکردن باسی بکەن ئەمە ڕوونە هیچ پرسیارەکەی لەسەر ئەم ئەسایمنتەش باش ئەگەر پرسیارتان نییە ئەچینە سەر لێکچەری دووهەم کە ئینترۆداکشنێکی تقریبان کورتە بۆ کۆمپیوتر تۆمۆگرافی. Okay. So let's switch back to English. I don't know, whenever I'm talking to like Kurdish, I just get used to it. So let's go back to the second lecture, which is a brief introduction to our course. And there's only like 2 slides at the end that I would say it have the important part of this lecture. Otherwise, this is mostly like a historical background of the course. So, okay. Let's go full screen. If at any point that you lose my screen or it's interrupting, please let me know, because sometimes that happens and I'm not aware of it, especially when we do the slide sharing and full screen. Okay, so introduction to the CT scan. We will basically talk about how CT scan works in a very short detail, because we will go over the detail like later, and advantage and limitation of the CT scan and the evolution. That will be the main part of this lecture. Evolution of multi-slice CT scan, limitation of it, and basically we will talk about dosimetry at the end. So if we look at the content of the course, now we are at topic 1. We are covering this topic. So each week that we will go to the next lecture, basically, I'm going to make this one green and the other one blue. So I think it will be easy for you to keep track of where we are. So, and hopefully by the end of this lecture, you will be able to define what a CT is, the cross-sectional imaging principle, and the physics operation. We will talk about it in a lot of detail. So, because that is basically the purpose of this course, the physics of CT scan. And for today, we will talk about the historical development and image planes and generation of the CT scans, which we have like 7 of them by now. So we will talk about those, and acquisition time, scanning time, and pitch. That will be the focus of the end with the dosimetry, basically. So the computed tomography, just by the name of it, that comes from like the ancient Greek, almost like a slice. It's basically like you have an X-ray, but multiple of X-ray, that basically like you're taking the sliced image of the human body, but then it is possible to manipulate that data to regenerate it in different Excel view, basically. So this CT scan produces a cross-sectional slice of the body. Then it allows us to visualize inside the body without basically cutting through it, which is a very, very good thing for the medical imaging that we have, CT scan, MRI, and all the other ones. So in this case, if we look at it, like I said, it produces a perpendicular, an image that's perpendicular to the long axis of the body. Usually like the body is like this way and it rotates around it to make a sliced image of the body. But then you can reconstruct it using like a computer algorithms to view it in different plane, basically. And the more data that we have, the more detailed the image will be. And historical background of this, that's Godfrey was credited for invention of the CT scan. And the first one was very, very slow. I require like up to like 9 days to acquire like a single slice image. And those two scientists later, basically, they received a Nobel Prize for their invention. But there has been a lot of development since then in the CT scan. And nowadays, like you can basically get the image in like a millisecond, so you can see that very, very big difference from 9 days to that. And any other development that happens is focus on the timing and the doses basically, and of course the quality of the image, but there gotta be like a trade-off between those, because if we have like a longer time of the scanning, we might expose the patient to more radiation. So there should be a trade-off between those, like a balance. Which one are we trying to focus on more? Are we trying to get like a more detailed image or faster image or something like that, or we keep the balance between those two? So if we look at the CT scanning like projection, this is usually the original view of it, the transverse plane basically. Then because like it goes around the body, takes like that slice, then moves the old way basically. It moves to the next slice and do the same thing. It moves to the next slice and do the same thing. Even the new ones basically follows the same procedure, but some of time the patient is moving and the coils can rotate like basically very, very fast to do it continuously like a helix basically. So, but then this picture that we have, if we get like a lot of data for this slice, for that slice, for that slice, for that slice, then we can reconstruct it in a different planes basically by using computer algorithms to view it in different plane, in this way, or sagittal, or let me just move this away a little bit to know. I don't know, let's put it right here. Or the coronal view basically of the image. But the original acquisition of the data is this, just to make that clear. Then we can manipulate it in the way that we want to see it in different planes. Okay. So the generations of CT scan. We have multiple generations depending on the detector type, the X-ray, and the computing power, and all those stuff basically distinguish between the generations. Okay, let's close this. Okay, so all this have been made, like all this development, because we want like a faster scan time. So, improve image quality and the resolution, enhanced image processing and capabilities. Faster, it is better in this case because you are exposing the patient into less radiation. And we want the image quality to be better and better, of course, and the processing capability of the computer and all those stuff affects that also. So, and what we want to focus on here, especially for the timing, what are those evolutions contributing in terms of reduce the motion artifact? Because if it takes too long, the patient might move. Like if you cannot do it in one breath holding, basically, the patient might move, then we will introduce in like a motion artifact. And the dose basically, and can this help for the image quality or improving the diagnostic accuracy? So all this improvement, the target is to focus on this. Okay? The timing and the radiation dose and the quality of the image basically. Okay. Do we have any question to this point? This we are just doing like some historical background of it. Like I said, this might be like a little bit short lecture for today. And if you want to get some break at some point, please let me know. I was planning to finish this in half hour or so, but we did the introduction, so it might take us like 15 to 20 more minutes. If you want to take a break, we can do that and come back again. Or if you want to continue with it, we can finish it, then you can have the rest of the day free. So who's with break? Who wants to continue? Okay, I'm not seeing and not hearing anything about the break, so we just keep continue. Okay, we have one person raised hand. Yes, go ahead, please. Okay, let me see if I can view it in different, adjust view. Go to dynamic. How will we do this way? Okay. So just to make sure, keep going, right? Finish it, then we can have the break later. Okay. Okay. So we will, yes, thank you for confirming that. Okay. So to get rid of this notation, I want to dismiss it. Okay. Stay there.
دکتۆر یازنە بە دوایی لێکچەرەکە ئەگەر بتوانی لە سیستەما داینێچکێنەوە سیستەما داونە نابوو.
PowerPoint?
بەڵێ. PowerPoint یان PDF کێشە نییە.
So it was not there? Okay.
No, system.
I will definitely do that. I thought I already uploaded it. So
No, it's uploaded already.
it was there, right? That's what I had in mind also. I don't know, like if it's not there, I'm gonna double check it. But if
I checked the system before and it's not uploaded.
Yes, it's not.
It's not. So if you check here, this is the computer tomography. If you look under, we have week 1 and 2. So week 2, okay. Oh, I see what happened. I did those introduction and lecture 1 together before, but then I think I updated the lecture 1 to only have the introduction. So I'm gonna upload the second one to week 2 later. Okay, thank you for letting me know. Yeah, I think it was there before with the first lecture, but then I updated. Okay, I see what happened. Okay, so the first generation basically, like I had like a pencil shape laser. Apparently this does not allow me to do it. I'm just gonna close it right here. Okay, we don't need it. Okay, so and the detector basically like the detector on the other side of it, and it was moving around like on when it was scanning, then move it. When it was moving, turn it off, then scan again, then move it, turn it off, then turn it on and scan again. So it was going like half of the circle basically, like, and detecting on the other side. So it took a long time, but it was definitely a good start. So it took nearly like 5 minutes to complete one slice, which is for that type of technology and that time For now, it definitely might look like it's a very, very long time, but at that time, no, it was a very good and advanced in technology, basically. So this is basically what happened. Like you have like a pencil-shaped laser, basically go through it, then scan it on the other side or detect it on the other side, and keep doing that. But while it was doing it, like turning the laser on and off, like off when it was moving, then on when it is scanning and detecting. So it was only designed for head, basically, at that time, to do the scan of the head. Then the second generation got a little bit better. Instead of having only like 2 detector, it was an array of detector, like almost about like 30 detector. Then it made it like a little bit shorter for the scan, because like the running time got shorter. So there was a lot of detectors here. But even though it got even better, like from like 10 to 90 seconds per slice. So it got, for the third generation, it is the same idea, basically. You have like a fan-shaped laser goes out, but it got better for the detector. It's like an arc shape, and the number of the detector grew way more, like from 250 to 750 detector. It was like an arc or curved shape, so it could go around the patient and detect more signals, basically. And this one basically had like a translate rotation mechanism, was replaced by the rotate mechanism. What does that mean? Like, like the translate rotate, basically you move, then change the angle, like move it, change the angle. This one was just keep rotating, like rotation mechanism. Even it got better, because with this, there was like a wires and those stuff was connected to it. Then it got a little bit better. This is the prototype shape of it. It got even a little bit better for the fourth generation, like the fan shape, and the detector got up to like 2,000 detectors. So, and it was all around. Like it was not only part of the basically arc or the curve, it was all around the patient, and the laser was moving around, so it can be detected all the way around. So, and the detectors was not rotating anymore. Only the lasers, the X-ray source was rotating, and the detectors were stationary, because if you just keep rotating the X-ray, and then it was detected by the detector. So this one got very fast, capable of 1 second scan time for a slice. So, and for the advantage of the fourth generation is the increased dose of radiation to the patient. This was basically the disadvantage of it, sorry, not the advantage. It increased the radiation to the patient and keep going around. One thing we could, it was later developed to reduce or basically eliminate or reduce that disadvantage, was having multiple array, especially for the sixth generation that we will talk about in the next slide. For the fifth generation, it was a little bit different. This one designed specifically for heart. There was like electron beam going around, targeted at the heart, and then taking picture. It was fast, but it was very, very expensive, and it was only designed for the heart imaging at that point. It had its own advantage, but it could get better. So in this case, this is what it's called, like the electron beam CT scanner. It was like the electron goes from here, then it was targeted as those coils, then it goes like if the patient lies down here, it goes specifically targeted to the heart of the patient to take the image of the patient. It was fast, but like I said, but it was like only designed for the heart, and it was expensive. So in that case, the sixth generation came in. This one was like a multi-sliced. And if we look at that, sixth generation, so slip ring technology, that was one of the disadvantage or limitation of the fifth generation. Like this one was connected by a cable. So there was only like specific number of rotations they could do with it before they have to unwind it and go back, like start from the beginning. Here, this one, they used like a slip ring technology. So basically, it was not connected by hard cable, so it can go around as much as they want. And it replaced the cable, so it has like a continuous rotation without needing for any unwinding. So cable, like before they had it, limited the scanners because they could only, like I said, go around certain, let's say, rotations, then they had to be unwind, otherwise the wires will snap and so on. So, and the X-ray tube circle around the patient table is continuously moved through the board of the gantry. So this one was allowing to take the scanning like continuously in the helical or spiral shape. So just like doing this and the patient was moving. So basically like taking each slice each time it goes around. So this was a very, very good improvement in the CT scan. And let's say if we see complete the entire exam with the patient like holding one breath. So that is very, very fast and basically decreases the motion artifact. So decreasing the motion artifact, that is a very, very good improvement if you focus on the medical imaging, because we want to avoid that a lot. So this was the sixth generation. But then again, there was a better way to do it. If you look at it like here, this is the sixth generation, spiraling around, and the patient just keep moving. So each time it takes like a new slice. So it will be very, very fast compared to the previous one. And it basically scans continuously, not only like one slice, then another slice, then another slice, like that before. Okay. So this is the comparison between XL CT scan and the spiral or elliptical. So several seconds per slice. If you look at this acquisition time, the time to acquire one slice, this is almost 30 seconds. This one, like the total examination time, like including the table movement and everything, because like I said, like you're doing one slice, then move, then do another slice, then move, then slice. But this one we're doing like continuously. So basically you could do the whole examination in one complete scan basically. So for each slice, this might, like for each run, this, you could say that this one was taking longer, but this was doing like the whole thing at the same time. It does not need like do one slice, then move, one slice, then move, and so on. So overall, this got faster compared to the one that we had before. Okay, so sorry. Yeah. So before we go to the sixth generation, seventh generation, sixth generation, because like we had those continuously move. There's one thing that we need to consider that has a very big effect of the image quality is the pitch. So what does that mean? Like how fast we are moving the patient and how fast the X-ray source is rotating basically. So the pitch is the ratio of the table movement to the section thickness. So when this source is moving, it covers like some section. Depending on the thickness of that section and how fast we are moving, it tells you, are we covering the whole area? Are we covering the same area multiple times? Because if the patient is moving very, very slow, that means we are covering the same area multiple times. That basically you are exposing the patient to more than radiation that it needs. Or if it moves very fast, then you are missing some of those. So for example, it starts from here, then the patient moves so fast, then there will be gaps between the slices. So you are missing some data. So depending on what you want to focus on, this could be controlled basically. So if you look at the ratio, usually, if you are doing like 1-to-1, what does that tell you? Like in one, if the slice is this thick, just for example, then the amount of the time that the X-ray source takes to complete one rotation, the patient moves by the same amount of the slice. So for the next rotation, it will have a new slice, new completely slice. There's no overlap, there's no repetition, or there's no missing gap. So that's 1-to-1 is basically like the optimal one if we want to look at it, because we are not covering the same part of the body twice, and there's no gap. If it is bigger than one, if it's bigger than one, that means the table moves faster than the rotation of the X-ray. So in that case, if the table is moving faster, so the X-ray basically cannot cover the whole body. So there are gaps in the X-ray helix. So, and in this case, you are exposing the patient to less radiation, but then there will be some missing data, basically. That affects the image quality to be reduced, because, like I said, there is some gap between the slices, but then the radiation dose goes down. Another one, if it's less than one. So what does that mean? If the movement is slower than the section thickness, basically, that means the X-ray source moves very, very fast, but the patient is moving very slow. So it will not move to the next slice for the next rotation. So you are covering, or the X-ray is covering the next, the same slice over and over. So there will be overlap between the X-ray. In this case, the image quality, because you are getting more data, so the image quality will go higher. But, excuse me, but the radiation dose also goes higher. So the radiologist has to decide in that case, are we trying to focus on the image quality here, or how much are we exposing the patient to the X-ray, basically. So in that case, there should be a trade-off to make that decision, but that's what it means here for the pitch. How fast the patient is moving compared to the section thickness. If it's moving with the same thickness, that's 1-to-1, then you'll get the same thickness of the section and the same movement, basically, at the same time. If it's more than one, the patient is moving faster, the rotation cannot cover the whole body, there will be gaps. If it's less than one, I need to take a breath. Okay, if it's less than one, that means the patient is moving very slow compared to the rotation of the X-ray source. Then we are covering the same area more and more. We are getting more data, higher or better image quality, but at the same time, more exposure for the patient. Okay, do we have any question to this point? Let me just ask that to see if everybody is awake. Do we have any question? No question? I'm still trying to figure out, even with the other class. Does that mean no question, or like some of you do that, no question? I don't know, like. So this is no question. This means what? We are good to go? Keep going? Okay. So we have, okay. Because the other class did the same thing, kind of like, it was new to me. Okay. The 7th generation, basically, instead of having like one array of detector, there was multiple of them, which basically made the scanning time a little bit faster. So this is the only difference, the multi-slice computer tomography. If you look at the previous ones, all those detectors that we have, like it's a single array, but then for here we have multiple array also. So this is the advancement for the 7th generation. So it reduces the exposure time, improves the image resolution, and so basically that is for the 7th generation. So the dosimetry, that is basically the end of this lecture that we want to focus on. So basically, two things I want you to remember about this lecture. Okay? Beside the historical development of CT scan, like generations. Sorry about that. Okay. Okay. So there's two things: the pitch, what does that mean, and the dosimetry that we will focus on, like how much we are exposing the patient to those radiation. So it's a measurement and assessment of radiation dose. Okay. That we expose the patient to during the CT scan. So the quantities that usually is used is the computed tomography dose index. That's for the single slice. For the volume, you have like the average dose within the scanned volume. Okay, and this is accounts for the pitch in the elliptical CT scan. And then we have dose lengths product, which is basically the product of those, how much we are doing per volume and multiplying by the slice. And those factors that affects the dose that we are exposing the patient to, it depends on the current that we are using for the coils, milliamp, kilovolt peak, that also we will talk about. That affects also, because it tells you the quality of the image. Are we exposing the patient to a stronger radiation, or stronger means like more energetic radiation or less energetic radiation? Are we scanning like a soft tissue part or like a very hard and bone tissue part? Because some of them needs more energetic, some of them needs less energetic in that case. So scan length also, patient size also affects those, like one of those factors. So in this case, you have to study like what are you focusing on to come up with what we call like a LARA, basically, as low as reasonably achievable. So this is basically the trade-off. Are we looking for the image quality? Are we looking at some patient that we cannot expose to more radiation? Or are we looking at an infant or like elderly or a healthy person? So for each case, the decision needs to be made like, this is the amount of the radiation that we can expose that patient to get good enough quality image out of it. If we do more, it might not benefit the patient. So those trade-off needs to be considered for those cases separately. And usually when you have experience with it, you can make that decision easily. So, and this can be done basically like by the lowest dose and automatic exposure control. And we have some things like a safety procedure that we have for the MRI. And if you are looking at a specific point for that body, just focus on that region and do not expose the patient to like a lot of unnecessary radiation and those stuff. And this basically, in terms of the clinical, balance the image quality and the radiation risk. So we have to consider that balance. Are we looking for the image quality? Can we expose the patient to that much radiation or not? So it depends on the health of the patient, the size, the age, and all those stuff. So, and we are trying definitely to avoid unnecessary exposure. And this is basically for the safety of the patient, and at the same time getting enough like quality image that we can use for the diagnosis. So for today, like I said, those two things are important to remember: what is pitch and the dosimetry, the focus of those. Otherwise, the rest of it is historical development of CT scans that we are using today. And that is the end of today's lecture. If we don't have any question, I'm going to take the attendance, and after that, you are free to go. Question or no question? No question. Okay. Okay. For next week, probably the lecture will be a little bit longer. So we will do like part of the lecture, then we can get the rest, and we do the rest of the lecture. So that will be the plan for hopefully next week. And if anything changed for the schedule again, because like this schedule, they only gave us for this week because they did not want to have lecture on Thursdays. So if anything changed, hopefully Ms. Shena can share it with you. But if I get the schedule at any time, I still have some of you messaging me. I'm gonna message to them and post it on here also, post the update of the schedule. So if you have it on the same time, probably you will not hear anything from me because it will be the same time. If we go back to the previous version, I'm gonna upload the previous version of the timetable here and update you on that. Okay, let's go ahead and take the attendance, which was supposed to be here.